Hello to everybody in class. Hello to everybody online. Good to see you in one form or another. Today, I'll do my best to have my audio captured so I don't have to re-record this in a bedroom in my house before my wife or child try to interrupt me and you start hearing me start to swear obscenities. And I'm just kidding. I try not to do that with them. Try not to do that with them. That would be really bad role model. So, a couple announcements. Formative assessment 7. Did you get the heads up? It's asking you about the two sides of a model. You can handle that, right? Sweet. I'll have a homework 3 for you tomorrow, hopefully. It'll be latent variable models, at least a very beginning part of it. I will grade your project part 1 soon, but I was going to ask or think about it. So what I had planned to do is spend the last week having presentations about your project, because I'd like for you to talk about what you did with your data, and even I'd like to ask you to share your stand code, not your data, but your stand code with people to show how you wrote it, as like building a repository of examples, because I feel like examples can be very helpful. Now, as we go through this class, as you realize, I struggle trying to figure out how to put all the Bayesian and all the psychometrics in. So I'm having this debate in my head, and I'm going to ask your feedback. We could spend the last week of class doing the presentations in class time, or I could lecture that last week of class, and we could just have a 3-hour session sometime in the finals week, sometime when we can make it, where we do the presentations. That would give you 2 extra lectures of stuff to talk about. Do you have a preference? The other thing, the benefit of that is the project won't be due until finals week anyway. You'll have an extra week to do it, prepare it, to do your discussion, and so forth. What do you think? The downside, of course, is it's finals week. But it's supposed to be, like, if we do it during finals week, I'll tell you what, I'll get pizza, or we'll have some food. We'll make it like more of a low-key, like, event, rather than that, like, to try to incentivize it. I just feel like we're gonna run out of time so fast that we could spend, 2 more class periods giving you some more material as we go forward. But what are your thoughts? I don't know that a vote's going to be good, because inevitably not everybody will be happy with it. What's your feedback on my thoughts?
The pizza come from the wedge.
Yeah. Tell you what, you just tell me what you like. Is the wedge, would you recommend that I take it?
Yeah, as someone from New York, I would say it's the best pizza.
I was going to say, okay, now again, none of us are from Iowa, right? What the heck is up with pizza here? I'm sorry, right?
They only believe in gas.
Oh my goodness, right? Oh my goodness.
But the wedge is the best.
I was on a search committee, and it was the Zoom search committees that we had during the pandemic, and people would ask, "Oh, what do you guys do? What type of pizza?" I was like, "Oh, don't get me started on pizza." And then one of the other professors' husbands is like, he's from France and loves making pizza, like that's his thing. And he's like, "Oh," so we were at a social event and I saw him. He's like, "I hear you don't like the pizza here." I'm like, "Oh my God, no." I mean, it's edible, it's fine, it's still pizza, right? Pizza's still pizza, but yeah, if we could do the wedge, I'd like to hear about it, because I have not found anything suitable for pizza here.
It's the only suitable pizza.
Okay, so question then from New York. Sorry, this is on you though. You have to answer this. What's your take on pineapple on the top of pizza?
I don't think that's a question from New York, but I'm a fan.
Okay, good. All right. Is it easier to come to consensus on whether we should have the presentations with pizza during finals week, or is it easier to say that we can have some pizza that doesn't have pineapple, or what does have pineapple? I think that, I don't know. Pineapple is a very divisive pizza topic, I understand, right? How many of you think pineapple's okay on pizza, or good? I'm there. How many is like, absolutely not, that's terrible? All right, there we go. So other thoughts on, yes, we could do wedge. We could just make it, like informal. I mean, still, it's a presentation, but the goal is, again, to get learning going on, right? Learning from each other. Does finals week sound okay? And would that be, is that an extra burden on you? So actually, I have to build a couple more lectures. Let me tell you, I'm literally like putting things together minutes before class. So, but I'm willing to do it because I want you to learn. Is that cool? All right. I'll go back. I'll think about it some more to make sure. If anybody dissents, that's okay. Send me an email. You can even get a burner email account and send it to me anonymously. It's fine. I'll be totally receptive. But I just thought, why am I doing this finals? Why don't we just move that to finals week? All right. And we'll have to find a room. We'll figure it out though. Or we could do it all by Zoom. Well, no. We'll do the same way we're doing now. Oh, I see a chat. A chat that says, vote for pineapple. Oh, pineapple and jalapeno. You're speaking my language. If you throw pineapple, jalapeno, and maybe some pepperoni on it, oof, yeah. And maybe a little bit of honey on top. No, I'm serious. Get the honey and the sweet and the spice. Anyway. No? Everybody's looking at me like I'm crazy.
Where's the pizza?
It's supposed to be after lunchtime already, right? Ah, yes. Please do try the honey with it. Get the sweet with the spice. And then, sweet and salt. Pizza has a lot of salt in it anyway, so it's pretty good. All right. What do you remember from last time? For me, it's like tabula rasa. Like, what did we do last week? We talked on the right-hand side. I remember that. I'm telling you about latent variables. And now it's time to deal with the left-hand side. So let me give you what's going to happen. Again, I'm always tinkering, always trying to find ways to figure out the right combo of things to do it in a general sense so we don't silo each of these types of methods. Today I have a lecture prepared where we are going to pause the right-hand side discussion and we're going to only do a single latent variable. It's kind of uninteresting, but it limits complication for the moment. So we'll have a single latent variable, and on the left-hand side, we're going to have normal distributions for all of our observed variables. Okay? And then we're going to take that, and we're going to break the normal, and we're going to do Bernoulli distributions and multinomial distributions, still with that single latent variable. And then we'll flip over and start doing some of the latent variable side stuff, meaning how do we identify the scale, and what about multiple dimensions? And then we'll get into the things we also have to do, such as model fit and scale interpretation and so forth. That's the plan. Any thoughts, questions on that? Welcome to Dissent. And again, you can get the burner email account. Send me, like, I dissent is the title of your email. That'd be great. This is not, even though it is sort of a dictatorship, I've got to run the class, I do want your feedback, all right? How's that sound? I do want to know. You're the customer, and the customer is always right. Oh, here. No, never mind. All right. I've got the energy at least. I feel like I'm energetic. Do you feel that in me? Maybe hopped up on caffeine. One of those is true. All right.
I mean, somebody's got to bring energy.
Oh, I'm trying. Nobody has ever accused me for lacking enthusiasm, particularly about this stuff. So at least I have that. This is what I'm calling Lecture 4B, Modeling Observed Data. It should be with normal distributions. But that's where we go. Oh, shoot. I started my objectives, and the lecture took way too long. You'll see there's 46 slides already. So the standardized versus marker item will be after we get through all the item types. So we're going to have this lecture today. It's going to set the mold. Actually, it's going to probably be today and Friday. It's going to set the mold, and then we're going to switch up from normal distribution to the other distributions I talked about. And then we'll get to the standardized or the marker item types as well. Because, as you will see later in the slides, and this is important, I forgot to tease the end of this week. I changed a random number seed, and all hell broke loose at 3:15 yesterday afternoon. That's it. That's all I want to tell you. One of you knows what I'm talking about because they were in my office and saw the picture. But the rest of you, what happened? Seriously. All right, I'll show you. Do you remember the data? We're using the conspiracy theories. You remember all those items? We did the alignment. The alignment stuff that we talked about the last time will come back when we get to multiple dimensions. Right now, the alignment is the dumb alignment. Everything measures one dimension. Okay? Okay. Remember our skewed data too? Okay. All right. So for today's lecture, we're going to assume each of the 10 items measures a single latent variable. That latent variable we will call a person's tendency to believe in conspiracy theories. Fair? Now that statement in and of itself requires a validity argument. We're just going to wave our hands at that. There are lots of ways of building a validity argument for it. We're not doing any of that in this class. So we're going to denote this latent variable with a theta p, like I've been doing through class. So theta is the score of the latent variable. P is a person for an index. And we will assume this latent variable is continuous. It is normally distributed. So this is the way I denote that. And for normal, has a mean, mu theta, and standard deviation, sigma theta. And I'm using standard deviation there because remember stan, when you put a normal distribution in it, it says the second argument is the standard deviation, not the variance, right? So, and then across all people, one thing I wanted to note was if we were to describe all of the people's latent variables, we could put them into a column vector. And I can denote that with a capital theta, with some boldface. And actually, I should probably have this capital not capital, but it's a boldface theta. We usually reserve capital. This is not always true, but in my syntax for notation, the capital letter in bold is a matrix, whereas the non-capital letter in bold is usually a vector. And this right now is a vector. But what we progress to, when we have more than one latent variable per person, then when we put them all into one matrix, that would be a capital letter, right? So, okay. Questions on where we're starting? How we're making it work? Yes?
In this case, you're assuming that this would be something like a CFA or IRT model.
Haven't gotten there yet.
Okay.
Yeah, right now I'm just talking about theta.
Okay, yeah.
And
But we are talking about the distribution of the latent trait, not the distribution of the item responsible.
that's right. Right now it's just the distribution of the latent trait. With it normal, we can't tell. It could be CFA, it could be IRT,
Yeah.
it could be item factor. Like the labels at some point break down.
Mm.
When I get to the next slide, you'll see. Okay? In fact, any other questions? All right, building measurement models. Remember the steps in the analysis? We need to specify the model, specify the scale, meaning the mean and the variance, estimate the model, examine model data fit, repeat until you get good fit, and then maybe do some other stuff with the results, right? Today is all about number one. Number two, actually number one and number two and number three, we're going to estimate the model. You're going to see today estimating the model. It's not as easy as blindly saying, hey, M plus, do this for me. It's all a little bit more complicated. It's just slightly. And once you know a little bit about it, it won't be that complicated. Number two on today, actually number one in today we'll have with the next slide. What did I tell you a model is defined by? It's a distribution, right, of a variable, and then what is predicting it, right? So like the linear component part and the distribution of the outcome itself. So we're going to do that part today. For step two, we are going to simply identify the scale with a mean of 0 and a variance or standard deviation of 1. We'll have a standardized latent variable for this as well because we're trying to simplify the process to show the model building on the left-hand side of the model now. Okay? Okay. So now, Vladimir, we're going to talk about CFA. What we would call CFA otherwise. We're going to model observed variables with normal distributions. In other classes that you might take, Lisa's teaching a class right now, like factor analysis and structural equation modeling, where the measurement models, to begin with, use normal distributions for the outcomes. We tend to call that factor analysis. I want to move you away. You got to know that term, but remember that it only goes so far. Okay? Right? Remember, it's distributional specifications. And someone says, I did a factor analysis. Heck, I have a grant with a colleague who was an associate editor when I was editor at JEM. Right? So really well-accomplished person. They do modeling correct, in my opinion. So nothing bad. But they said, oh, I did factor analysis on these data. They were binary data. Oh, it was item factor analysis, which I would call IRT. So remember, when you say I'm doing, and you put a label in, it gives the big picture, but you need to be more specific, and that's where, what are the distributions, what are the assumptions that go from it, okay? So, what are we doing with our lives? Where are we going with our life? I always ask myself that question, and when you're young, that's appropriate. When you're middle-aged like me, it's like a midlife crisis. Where am I going with my life? What am I, no, just kidding. I'm going to talk about this with enthusiasm. So, we are, our psychometric model, a psychometric model posits one or more hypothesized latent variables predicts a person's response to observed items. Remember that, right? It's, if we could observe the latent variable, we're putting it in a linear model to predict an item response, right? Somebody who's high on, somebody who has a high level of a tendency to believe in conspiracies is likely to rate each of these items very high. Some are higher than others. Some conspiracy items are easier to believe than others, right? But that's what we're talking about. So today, that's the tendency to believe in conspiracies. It's one variable, it's unidimensional. So we're going to take all 10 of those items, and we're going to have a model for each, where each one of those 10 items is being predicted by the latent variable as if we had observed it, right? So this is a very simple linear regression approach. Yes?
So I had a conversation today morning with someone, and why we are arguing linearity of the models always for all different types of models. So why don't we use like polynomial models?
We could.
Or any other types of models?
We could. In fact, if you think about it from a linear model's perspective, there's nothing that says you should have a linear prediction of an outcome, even if it's link transformed, right? Like logit or otherwise. There have been, actually in the 1960s even, people worried about this. Was as soon as they started thinking about this in a general way, the person I learned a lot of this from, Rod McDonald, who's, I think I've had his book chapters, one of his chapters assigned in here. He had a monograph in 1967 on nonlinear factor analysis. You could do that. Alternatively, you want to go a step further. If you think about if you have a model where you have multiple latent variables, and you have two latent variables being measured by an item, in what we do mostly, those are main effects. But there's nothing that says they couldn't interact, latent variable interaction. And that latent variable interaction, if you think about the prediction, it is a nonlinear prediction, because the interaction is moderating each of the main effects, and so it gives a curvilinear version of the main effect based on the values of the interaction itself, right? You don't see that either. You could. Actually, you see it. Diagnostic models and in some parts of factor analysis literature, but not a lot. So the answer to that is, I think people, let me give you my belief. This is hypothesis that needs to be tested. But one of the reasons for it is the way that we teach this is so separate. This is CFA, this is IRT, this is whatever, that we tend to lose sight of the generality that underlies it, right? And the second part of my hypothesis is that when people learn a method, like if you're in a field where you're using that method, so for instance, educational measurement, generally you're using something like IRT or some other test theory-based method. Like you are going to focus on what's common in that area, not the generality as well. So those are the reasons why I don't think. That's a very good question.
What about the interpretation of the model? In the other cases, I mean, non-linear models.
Hard. Also hard. Yeah, it can be very difficult. The interaction models I found to be easier because I'm used to interactions in linear models. But yeah, there could be all sorts of nonlinear effects going on that we don't know about. It's a very good question. Yes?
Well, kind of following with that, so if we have reason to believe like that slopes are not constant, like lambda is not a constant value for everyone, then would that justify maybe doing like a quadratic relationship between theta and
Possibly.
the outcome?
Possibly.
Okay.
Depends on the design, right?
Okay.
If it's not constant for everybody because there's some other unaccounted for latent variable, then yes.
Okay.
If it's not constant for everybody because of some other factor, like in a like a multi-level design, there may be a different way of making it non-constant. For instance,
Yeah,
making
well-
it a random effect.
Like, and I sent an email to Lisa about this morning too, because I was.
I know, she posted it on Facebook already. I'm just kidding.
Oh.
By the way, she would never
No,
do
I
that.
know.
Never, ever. I'm just teasing. I just want to be clear.
No, I know.
I stick my foot in my mouth too much.
I wouldn't care either.
No, no.
Even
I'm
if,
just kidding.
Because I asked like about, when do we add a random effect versus like going a nonlinear route, and so like just using the same example, so like
Mhm.
if we like learning curves, like people who just take off,
Mhm.
or maybe the other way around, they slow down at a certain
Right,
point.
yeah.
Then you could say, well, maybe theta is not, the
Yeah.
relationship between the outcome and theta is not linear. Maybe we should fit some sort of, non-linear thing.
Absolutely, yeah.
Okay.
Yeah, there's all sorts of ways of thinking about it. And this is why research in this area is open. You can do a lot with it. I had a former student at Kansas who did an MERT dissertation with interactions between the latent variables and saw some really interesting features of that, right? And so there's all sorts of ways of trying to incorporate that if you're interested in it. It's a wide open field. So, yeah, and I apologize. I hope it was clear that
Yeah.
I'm told by my wife and my children that I'm really bad at sarcasm. Like they can't tell when I'm joking, and I'm like, that's the subtlety. I'm high on subtlety and sarcasm, and that interaction means you think I'm bad at it. Non-linear. Anyway, sorry. See, that was subtle. Anyway, if I really wanted to say something, I'd be like, 'cause she's on TikTok, which I don't even think we have TikTok. So. All right.
TikTok's going to be the new Facebook. That's a different subject.
Anyway, I try to stay off of all of it because I like to keep my mind clean, or at least distraction-free, and that is hard enough. So again, we're going to assume today each response follows a normal distribution. So think about that. Take a look at these data. 5 categories. And again, you have to sort of look sideways at the data. Everybody bend to the right. Just look over there. Does that look like a normal distribution to you?
Absolutely not.
Okay. Now, you will tell me, hey, Templin, you told me before in linear regression world, it's a conditional normal distribution. And I'd say, yes, given x, because we're not assuming a distribution of x. But today's different because we are assuming our x is theta, and we are assuming a distribution of it. By the way, yes. That was for my son. All right? All right? Okay. That's his like Halloween costume, although it's green, but
I love that.
So yes, we're still assuming a distribution that's normal, conditional on an outcome. Our outcome is not observed. But because it's not observed, we have to give it a distribution, and it's normal. So it turns out when you take a normal distribution of theta, and you take a normal distribution of error, and you add them together, you get another normal distribution. And when you add those two normal distributions, so what you end up saying is, with this assumption of the latent variable being normal, and the error or the outcome being normal, we should expect the data to look normal. And by normal, I mean symmetric, unimodal, all the things that if you bend your head to the right, none of that works, right? Right here. And that is why normal is the sus imposter. No. Is that right? I've only played the game a few times.
I've tried the game. It's different.
Yeah.
A person is just sus.
Okay.
Sus, yeah.
So CFA. CFA is sus.
Yes.
So let me ask you the question. If we know that, like if you pull up any journal where people are doing research with Likert scale items, almost any one of them, one of the papers, like take an article from this month, you'll see this. Why do we do it?
Because it's easy.
Yes, it's available and easy. But we're not here for easy, and CFA is sus. How about that? All right, so here's the model itself. We're taking a linear regression. We're doing for the whole thing that we did in linear regression previously, right? So basically, our outcome is y, our predictor is x. Now x is going to become theta, right? You have an intercept, you have a slope. And then we also have a residual term that follows a normal distribution with a zero mean and a standard deviation sigma e, right? And we saw from the last, like the first 6 weeks or however many weeks of class, how to build that in Stan. Putting all that together implied that the data followed a normal distribution where the mean was given by the conditional mean of the line that was above, and the standard deviation was given by the standard deviation of the error in the line above, right? So this is going to look very, very, very familiar because we're doing this 10 times. We just changed the notation slightly, right? These are all the 10 observed variables in our data. Each one has a mean or an intercept. Each one has a slope. Each one has an error term. That error term follows a normal distribution with a zero mean, and here I actually made it the variance itself. But now each of these terms has a different label, but they are the same, and we interpret them the same, okay? So what are those labels? Mu is the item intercept, just like we called it beta 0 before. So wherever in your brain exists a set of neurons or whatever that contain beta 0 and what it means, now just link it to something that says mu for an item, because that is the same, okay? Same thing as we interpreted before. It's the expected score of an item when the latent variable, in this case the single predictor we have, is equal to 0, okay? Lambda I is what we call the factor loading or discrimination. Depending on which camp you come from, not camp, which discipline you learn this in. In factor analysis, factor loading. Item response theory, discrimination. They are the same, right? It's a slope multiplying a latent variable on the linear part of the model equation. And we interpret it the same way as we interpreted it beta 1. There are some additional interpretations that we'll get to once we get past all the models. For instance, it's like the covariance between the outcome and the variable when you define certain things certain ways. But again, it's the expected change in y for a 1 unit increase in theta. Now that makes you ask the question, what's the units of theta? What do I mean by units of theta? It's another way of saying, what's the scale? What's the standard deviation of theta? And remember what we said we're going to set it to today? 1. So when I say a 1 unit increase in theta, I'm actually saying a 1 standard deviation increase. For every additional standard deviation in theta, we expect the outcome to go up by lambda I. But that is consistent with linear models. All right, now, if theta's standard deviation was not 1, which we'll see in the marker item case, then 1 unit in theta may not be 1 standard deviation. But it's really convenient to use standard deviations. You remember in linear models what we call those parameters that were in units of standard deviation? Standardized parameters. And we can do that too. So we're going to see all of that as we go forward. How we doing? All right? So literally, all that stuff before, you ever watch Karate Kid, like the old Karate Kid? Actually, so can I give you a story? You know the guy who came to observe me last time? I paid him well. Made sure he was. But it's sarcasm. I don't know if you know this about him. He was a karate athlete in Argentina, like world class, right? Like Pan American Games, almost Olympic level, right? And he's thinking about teaching his sons, like his sons are ready for karate, and he's like, well, I got to tell you though, you got to go through all the defensive maneuvers first. I'm like, oh yeah, like wax on, wax off, right? Or paint the fence, right? Or something like that, right? It's not just sweep the leg. It's all this other stuff. All that stuff we did before was all that, the wax on, the wax off of this. Now it's going to be somewhat easier, okay? I've given you Karate Kid, the old reference, Facebook. I've got a Among Us reference. What else you gotta feed me some references to try to get in here because I'm not cool anymore. I don't know that I ever was cool, never mind. All right, finally we have a last term. This term right here, the error variance itself. Before we call it residual variance, I guess with Stan I had to twist my arm and call it residual standard deviation. In factor analysis, this is called unique variance, right? Which means it's the variance unique to the item and not common to the factor, something, right? That term, unique variance, is what we'll call, and in Stan we'll have to specify it without the squared part. So unique standard deviation, which still sounds a little weird to me, but it means the same idea. It's just a different metric, okay? So what did we use the residual variance for last time? When we estimate a linear model, if this was observed, we'd look at it and say we could use it in part to talk about R squared, right? Model fit. Well, R squared, model fit with one outcome. You know, the model fit gets more complicated when you have more outcomes, but yes. And we could do the same thing, although it seems a little weird. I'm taking this thing I didn't observe, and I'm going to tell you how much the thing I didn't observe accounts for the variance in the variable I did. That's like saying the ghost in the room is really causing all this variables variation, right, or something along those lines. But we can quantify that as well. So, how are we doing? Any questions on this so far? All right, so this is the assumptions of confirmatory factor analysis, right? This is 100% confirmatory factor analysis, although I'm not trying to call it that, because again, I want to remove the label from what we do. If I added one item that was binary and we treated it with a logistic regression, now all of a sudden it's not all confirmatory factor analysis and we don't know what to call it, right? So, all right. So, yes?
I have a question. So, in the way I learn statistics, we usually call the models for what they're doing. So we either do a logistic regression or a linear regression. But here, I've heard people say you have to run an IRT, and to me IRT is a theory, not a specific model.
Yeah, that's right.
I'm very confused. Is this a CFA or is this multiple linear regressions?
They're synonymous. They mean the same thing.
Okay.
And I'm really glad you asked that question because I agree. Item response theory is a theory. There's no logistic to it, right? What we're doing with this assumption would be like doing 10 simultaneous linear regressions. Okay? And in fact, if I go back to this right here. So this is like a multivariate linear regression. Sometimes if you took multivariate statistics, you may hear of multivariate regression. Another place you may have seen this is a path model or a simultaneous equations model. Those are some of the other labels that go with it. But the big difference, again, is that we didn't observe the predictor. And so that's why I think we start saying it's factor analysis, because we have the latent variable is called a factor, and that's somehow it's doing this. Does that help answer your question? Very good question. Thank you for asking. Yes?
Would this be a 2PL model?
Yes.
Okay.
Yeah, that's the funny thing. Well, there's no L.
No, yeah, 2P.
Yeah. The L for logistic, unless you want to say L for linear, 2-parameter linear model, and then yes. But yes. Well, think of it this way. Actually, it's not. So it is and it isn't. Depends on what the 2 stands for. In a logistic regression, this term doesn't exist.
Yeah.
Technically it does. We just don't include it because its variance is a constant. Pi squared over 3. Well, times a multiple, we usually use that multiple as set to 1. All right? So in that regard, we actually have 3 parameters per item here. But one of them is on a side of the model that doesn't actually involve the mean. Right? If you go back to our specification, the variance or the error term shows up on the variance or standard deviation part of the model that doesn't exist in IRT. So if the 2 refers to the 2 parts of the linear model, then yes.
Well, the discrimination difficulty.
Because here we have a slope and an intercept.
Yeah.
But if the 2 refers to the total number of parameters per item, then no. It just goes in a different part. And that's the problem with the labels, because in the IRT world, when you have binary data, you won't have a variance, right? You'll have just the mean, a function for the mean. Or you could pick the variance and model it, but nobody does that, right? Does that make sense?
Yeah.
Yeah. But
Because this is CFA that we're doing right now.
that's
Okay.
linear regression. It's a normal distribution that we're using right now, and the normal distribution has two parameters to describe it. Cool? It's a tough thing to think about. It's like generalized linear models, but then with factors, right? And I know Lisa teaches that course, but not everybody has the chance to take it. But that's why that course, we think, should be like the second course you take in grad school, which is, all right, now that you've learned a little bit about linear, the right-hand side of a model, let's talk about the left-hand side and change up the distributions. So, all right. Other questions? How's today going, by the way? Is the pace good? These are great questions. I encourage more and more of these because it is weird. Trying to fit this into your existing, what you know about statistics or psychometrics or whatever works, measurement, whatever you want to call it. All right, so what we just did on the last slide, in the last few slides, was we specified the model. We defined a distribution for every variable and what the function of the mean of the outcome was equal to. Don't mind that. Remember the last week's slide? On the left-hand side, I had f of the expected value of y given theta. Well, here, we have to look at it, but that's the mean right there. So that's the mean right there. And because y is continuous, the function is a number 1 times the whole thing, something called the identity link. It means it doesn't do anything to it. 1 times the quantity is just the quantity, right? Okay, so for each of these, this is where I need this. Dang it, not that. U, there we go, right? When we say y equals mu I plus lambda I theta p plus e for person and item, what we're saying here is if we put in this, the function of the expected value of y given theta is just equal to 1 times that expected value of y given theta. This is a 1 right there, right? So that's just saying it's just the expected value of y given theta. And so when you apply that to this linear model right here, the expected value of y given theta is looking for this expected value of mu plus lambda I theta p plus epi. Now we can do a little bit of algebra. If you're used to statistics, mathematical statistics, this is what we call the algebra of expectations. We can distribute the expectation through this linear component. So this is equal to the expected value of mu plus the expected value of lambda theta p plus the expected value of error p, right? The expected value is another term for mean. What is the mean of error that we defined?
0.
0 by definition, so that goes away. Right? The expected value of a constant, right? If you have what's the mean of a number? It's just the number, right? Well, mu is a constant here, so this is just going to be mu. If you have a constant times a variable, that changes the expected value to be the constant times the expected value, right? And now, what we're left with is our model defined, effectively, right? Now, technically speaking, we just didn't condition things on theta. We had to actually have this, leave this as this expectation right here is not, I had the given theta part. I didn't say that before. So once we give each other theta, once we have the given theta, we're no longer saying it, we're recognizing its distribution. So I made a mistake on the fly here, but that's why it still shows up. So the expected value given theta is that right there, that linear term, and that's why it shows up in our model. So going back to last week, the function is the number 1 times everything. The expected value is just the mean, and then our linear model for it is given by the mean being the item intercept plus the factor loading times the latent variable. See how it connects? Okay. The next step, though, is to figure out the scale. We always said before we're using standardized latent variables. So theta will follow normal distribution, mean of 0, standard deviation 1. Standardized latent variable, the word standardized usually shows up with anything that has a mean of 0 and a variance or standard deviation of 1. So that's why it goes there. And because we add that normal there too, you can think of these as z-scores, like z-scores, right? It's a convenient metric for thinking of it. All right, questions? Now we're going to step 3, estimate the model. This is tough, right? How many of you hate Stan? It's okay. If you want to see JAGs, how many of you hate JAGs? JAGs is, after using Stan, I'm like, yeah, JAGs is painful. So it only gets worse from here, but let's do that. So there, you remember we culminated Stan with all sorts of craziness, right? I ended with a model matrix that we inputted into Stan, and then we had a matrix product with all the regression coefficients. The model matrix in this case can't be used. You want to think for a moment why. I'll give you a hint. X in our model is theta. We didn't observe X, which means every iteration, X will be changing. Maybe not for everybody, but it will be. So it means if X changes every iteration, we would have had to create a brand new model matrix in every iteration. And by the way, I wrote a package called Latent. It does that. It uses model matrices. I'll talk about it in EMS Pro Seminar on December 2nd, I think, about how Latent works. So at the end of this class, you'll be able to see me talk about how I built Latent to make this work, although not with Hamiltonian Monte Carlo. So we can't use the model matrix because every step of the chain, the model matrix is changing, right? Remember that continuous predictor was a column of X, right? So we have to change that. So we can't use a predictor matrix. We're going to import data as a matrix, right? Before we just had a column of Y. Now we have 10 Ys, right? So instead of having a column vector of Y, we'll have a matrix for Y. And then each set of the parameters will be specified as a vector. Now remember, in the previous class, we had one outcome and a bunch of coefficients for it. And we used a vector for those coefficients. But now what we're going to do is change it up a little bit. Each outcome is going to have its own set of coefficients. So we're going to just create vectors of coefficients to keep track of what those values happen to be when we build our model. All right? This also means two things. Each item has its own set of parameters. And we have to think about that when we specify our prior distributions for our parameters. By the way, today will be ludicrously uninformative priors. In fact, you can quote me on that. Ludicrously uninformative priors. Or redonkulous. You like that word? Is that too old? No. Okay, back.
You're dating yourself a little bit.
Redonkulous?
Yes.
Well, you want? I'm thinking like Spaceballs, ludicrous speed. You ever watch that movie? Okay, maybe next time. This is not off color, but never mind. Never mind. It's not funny now, but when I was growing up, that was amazing. I was like, Mom let me watch Spaceballs. Wow. Anyway. All right, the data block. Let's go through this real quick. Before, we had the number of observations. But now we need to tell Stan how many items we have. And we're telling Stan how many items we have because we're importing our observed data in a matrix that has items in the rows and observations in the columns. And so if I flip over to my R syntax real quick, what you're going to see right here is when I build my model data, this is my matrix that I'm importing. Right? So each column is a variable. So each column is the place of y from our previous syntax, whereas each row is a person. So we need to tell Stan how many columns we have in our data. Right? So far, so good? So now things get a little bit more complicated. With each item having just one latent variable, that means we know each item will have its own item intercept, mu. Each item will have its own factor loading, lambda, and each item will have its own residual or unique standard deviation, psi. So I split each of those up into 3 different parts. And actually, I'll flip forward for it. Here's our parameters. We have a theta for every person. We have an item intercept for every item. We have a lambda, or item factor loading, or discrimination, for every item. And we have a unique standard deviation for each item. So that's how I'm parameterizing the model. And you'll note the vector here is a little bit different than what we did in linear models. Remember, in linear models, we took the intercept and slope and put them all into one vector by itself. We don't have to do it that way. Here, what we're doing is taking each type of parameter and putting it in a vector by itself. So that means if there are 10 items, there are 10 intercepts, 10 factor loadings or discriminations, and 10 unique standard deviations. So now we're going to go flip back and see this last bit of code here. We can use that at the end of our linear model section when we had beta as a vector of coefficients. Its prior distribution was multivariate normal. And I mentioned that, said this several times, which really meant that each single parameter had a univariate normal prior distribution. And that's what we're going to do with mu and with lambda. So you remember the multivariate normal? There are two sets of parameters. There's a vector of means and a covariance matrix. The diagonal of the covariance matrix is where the variances are. The off diagonal is the covariances. So for us, we are going to have to give Stan a mean vector, right? One mean hyperparameter for each parameter. And a covariance matrix where the diagonal is each parameter's prior variance. And the off diagonal may be the prior covariance between parameters. Now that latter part, I don't know that I've ever seen it done in practice. It's almost always 0 as a prior value. Okay? So mu and the covariance of mu are what we call matrices of hyperparameters for the prior distribution. Remember the term hyperparameter? It's a parameter of the prior distribution of some other parameters, right? In our case, mu is a parameter in our model. We say it follows a multivariate normal distribution, so all the terms in that multivariate normal are hyperparameters. Remember that? It's a terrible name, because we could have parameters on the hyperparameter. We could have priors on the hyperparameters too. Never mind. It starts to go crazy pretty quick. We can't use a multivariate normal distribution for the standard deviations because they're bound to lower at 0. So for them, you remember which distribution we used in the linear models as a prior for our exponential? So here we just need a series of exponential rate parameters, and we need one for each item. Yeah?
So I've been looking through Stan code a little bit lately, and I've noticed they also is it Cauchy?
Cauchy, yeah.
Cauchy.
Uh-huh.
So what's the difference between an exponential prior and Cauchy prior?
They're wrong and I'm right. No, there's some differences in different parts of where you look at it. There's been, so in circa 2005 to 2012, there was a big battle about how we should put priors on standard deviations. Battle being an academic tiff. And there's sort of multiple camps of people on this. Some believe use uninformative, some believe use some type of distribution. And the sort of the things that they think about. So Cauchy is one of the responses to the uninformative prior. It still can be uninformative, it just has a certain form to it. The key in thinking about it is, one of the arguments was, well, for certain priors, if you were to transform some of the parts of the model, the posteriors wouldn't transform identically. Like it's not unique under transformation, so that was a problem for people. I think, generally speaking, what we're trying to do is put some prior on there that's a little bit more flexible than uniform, because we may need to stabilize a parameter estimate, but generally speaking, make it uninformative for right now. Does that sound good?
Yeah.
Any other questions? All right, so here is our parameterization. I'd mentioned this before. One thing I want to note that we never think about when we use factor analysis, and I say that because if we use a program that does factor analysis, like Lavon or M+, or pick your favorite, what's in Stata? The SEM in Stata.
The commands SEM.
SEM, fair. Turns out, if you look at our parameters, if they're allowed to be anything, we define our model as lambda times theta, and that influences the mean of our model. But it turns out lambda times theta is actually equivalent to negative lambda times negative theta. What does that mean? Right? They give you the same values. And so why this is important in the Bayesian sense, remember we're sampling from a distribution, and we have to start randomly where we sample. And it basically forms two modes of a distribution, two big, you might see something like this. Darn it. The posterior distribution of these parameters might look like that, where one might be, if this is 0, one might be lambda and one might be negative lambda. This, by the way, I'll just give it away. This is what happened at 3:15 in the afternoon last night.
Uh-oh.
Right? So in Bayes land, because we're sampling, where you start for algorithms depends on where you go for a mode usually. Because what ends up, even with Bayesian sampling algorithm, is once you start to head where the mass of a density might be, there's no easy way with most of the statistics that we build for you to go and jump to the other side. Right? So where you start governs where you end up. So what do you think happens with 4 chains? If we start right here, or somewhere randomly around it, we could quickly get some of the chains over here and some of the chains over there. Right? And you don't see this in software where someone has hard-coded all this, like in M+, or in Lavon, or any of the other parts of what you do, because they usually start things in a mode that makes sense. Right? For us, I prefer the positive theta. It's equivalent to have negative lambda and negative theta, but now it's no longer a theta. The more theta means less of the tendency to believe in conspiracies, right? And so when you have less theta, we offset that by a negative lambda, and the model works out to be the same. We never talk about it, but there's 2 modes for everyone, at least 2 modes for every one of these distributions. We have multiple latent variables, so there's even more of them, right? There's like 4, or if we have 2. So, caution. I say that because, literally, I use the starting number, random number seed, that one right there. This is the day I started my slides, October 9th. Back in the day, 16 days, 17. And then yesterday was October 25th, and I was continuing the process. So I said, I'll just update the random number seed. Bad. Anyway, yeah.
Can you restrict?
Yes. I'll have a fix for it at the end of slides.
Okay.
And actually that fix is under construction, so I'll have a better fix for it on Friday. So if you may have to re-download the slides Friday, but there'll be some additional slides on Friday that show how do we do that. All right, but that's just a heads up. When you build this, just remember, there's an additional, we are literally working with the core of what Psychometrics does, which is really cool if you think about it. Because if you learn this stuff the way I'm hoping that you'll learn it in this class, that means any type of model that someone throws at you, you'll be able to understand it. You may even be able to build it, implement it, and do it. But then you also have to see where the pitfalls are. and why things show up certain ways. All right, let's talk. Other questions on what I just said? Yeah.
Well, if you restrict, because you can have a negative loading.
You can. And
So would it just change the interpretation of?
we don't want that to happen.
Okay.
Because look at how we defined our model. We defined it on the positive side.
Mm-hmm.
So we defined theta as the tendency to believe in conspiracies. And if you get negative and don't realize it, you have completely changed the interpretation.
Yeah. Oh, I see.
Right? So it's really important that you, when you're going into this, realize that it's possible, and dare I say, probably more likely than not, depending on how you specify certain things, that you may get that. But here's the other complicating factor. And there's a lot of disagreement in this, but this is why, if you see, started in Bilog, but people who are in IRT world, for discrimination, often like prior distributions that restrict the range to be positive. Because now the parameter can never flip negative. Can you see any problems with that approach? I'll tell you one. If you have an item that should have a negative parameter, you want to know that, right?
Mm-hmm.
It may not be, depending on how much data you have, it may not be right at 0. It may be, oh, this is a very bad loading or something, where it may be indicative of some other problem with the item, or an item that really is operating in opposite of what you think it is. So the ability to estimate negative loadings, I think, is an important feature in a lot of what we do.
Mm-hmm.
But the fix for it, often in psychometrics and Bayes, is restrict the range of the parameter to be positive, which eliminates all the negative loadings. So here, I'm going to give away what I'm trying to build for Friday. What we have to do then is we have to go and ensure that our starting values lead to one mode. If we start on one side, remember I told you, as soon as we get, like these modes, the mass of a distribution is like mass of a black hole, right? Once you get pulled into it, you don't leave it, usually. Unless, again, there's certain algorithms that will force you to try to change mass in the middle of. These are usually machine learning type algorithms. We don't usually do that for what we're doing here. So what we want to do is start closer to the center of mass that fits what we think the model is defined as. The key is, in this case, for us, these two models are identical. They're equivalent. But because we've defined things to be positive, we should keep them positive. That make sense?
Yeah.
It's an interesting thing. You never talk about it. That's the other thing, like when you get into Bayes, I never thought about that part. I did think Rod McDonald was very good at talking about wanting negative loadings. He convinced me. Of course, I was young and naive, but, you know, now I'm old and naive, and I still believe it. Yeah.
One last thing. So if you have like the two modes, are they the same magnitude?
Yeah. Oh, you're going to see it.
Okay.
Like if you flip ahead to the slides, like slide 30 something, I call it like convergence fail, right? Two of the modes were positive. Let's just say close to 1 and positive. And then, sorry, 2 of the chains. And 2 of the chains ended up negative at the same value, real close to 1. And so the mean is actually very close to 0 if you take all 4 and look at the EAP estimate. But the R hat is huge. Like, wait a minute. The between chain variance is very large, but that's because they're reflected about 0. So it's a very interesting phenomenon you don't really hear about in other worlds of psychometrics. But if you're coding things and you're building algorithms, this is really important. You have to make sure things head the right direction. You also have to do things in a way that's still legitimate, right? There are legitimate reasons why we want random starting values. Because there are other distributions, there are other models where there are multiple modes that aren't reflections, right? And we want to know if we get into those. We don't want all of our parameters to end in one mode. So if we randomly start, we have to understand whether a mode is a reflection, which just means an opposite direction, or a mode is really a different part of the bubble of the likelihood or the posterior density that we're sampling from. Those other models where that happens are mixture models, generally speaking. Those are the ones we code. Stan's not really good at mixture models. And actually, when you read Stan's code, like you can, but there's like in Stan's user guide, it even says mixture models, because of the multiple modes, they're really not easy to do in Bayesian statistics because chains will flip, things will flip. How do you separate them? So, how are we doing? Too much? Okay. Other questions? No? Okay. Model. Finally, the model block where the fun happens, right? The vector lambda follows a multivariate normal distribution where the mean vector is what we input and the covariance matrix is what we input. That's just like beta from the last slides that we had. The vector mu follows a multivariate normal distribution where the mean vector is what we input and the covariance matrix is what we input. Again, that is just like the last set of slides, like the beta in linear models. Psi is a little bit different. Last time we only had one psi parameter. Now we have 10, right? One variance, one residual. So we still can just do psi, which is exponential, but Stan is coded in a way, they actually call these overloaded functions. I don't know if you've heard that term before. But basically, so long as the term that's in the parentheses matches the type and the size of the term that's out over here, it works. So psi is a 10-element vector. Psi rate is a 10-element vector. So what it does is it takes every element of psi and gives it the corresponding element of the rate as its parameter throughout. So it shortens the code a lot to build it. Right? For those of you, again, I'm not a professional coder, but I like coding. So, overloaded functions are functions that take different types of variables on input but still provide the same work. So this is like a vectorized function. It works with the vector, it works with the scalar. I don't think it works with the matrix though. So, any questions so far? Those are the priors. I haven't told you what I'm specifying those priors to be yet. Theta is a vector, right? There are the size of this number of observations is equal to the number of observations. There's 177 people in this data set. So theta is 177 length vector. And we fix its mean and variance to 0 and 1. I didn't even put those in as variables. And the reason I didn't put those in as variables, because when we start looking, if we ever want to change our prior, so say we get some non-convergence and we need to make things more informative, we will never ever change the hyperparameters of theta. This is the standard, this is our scale. So I code that hard-coded into the Stan code itself to sort of say, no, that has to be there because we're defining theta in that way. It's by definition. Right? We can change all the other parameters. Don't touch theta. Cool? Theta is, to the psychometric world, special. It's our factor score, our latent variable, right? All right, finally, for each item now, I have a loop. And for that loop, I say each item, so here, just go through the loop code. By the way, when I do my loops in my code, I don't like using I and J and K. You know why? Someone else has got to read your code. If you have to make them wonder what I is while they're trying to figure out a line of code, it's bad practice, right? So I encourage you to name your loop after what the loop is over, because you can name, it's just a variable in the system. So for item, in 1 to the number of items, I go and I model. Now remember, Y is a matrix, so when I specify the second element in the brackets with that looping variable, it's that column of Y. Right, so this takes one column at a time, says it follows a normal distribution for each of those columns. And now that normal distribution has the mean given by the mu, the item intercept for that item, plus the item factor loading or discrimination for that item, times theta. And you'll note the brackets by mu and lambda are different from before. Before in the linear model we had x times beta, the end. Here we have to specify mu plus lambda to make it work. I mean, there are other ways we could have put this in a matrix. I chose to make this a little bit more transparent here as we're building it. Right? So what that's doing is taking each item's respective item intercept and factor loading or discrimination, multiplying it by the latent variable, calling that the mean. And then on the other part of that, where the standard deviation goes, I am giving the psi parameter, or the unique standard deviation, with brackets so that each item's standard deviation shows up there. How's that work? Questions on that? So literally, this is a CFA model, but none of my code says CFA. Right? It's the building blocks of what we have come to call CFA. Right? And it will quickly, we'll see that we'll get out of what the label means when we start mixing and matching different distributions coming up here. Okay? Any other questions? Awesome. Let's choose some prior distributions. So there's a lot of bad ideas about priors. I don't use that term for a lot of what we do, but here I will, okay? Remember what happens when you use an informative prior. The parameters tend to go towards the center of that distribution, particularly when you don't have a lot of data. And we saw in our last example with 30 observations, we could put a informative prior on the betas and everything went crazy, right? Same thing happens here. But here's the key thing. If we're building this model because we're really interested in the person's theta, turns out the posterior distribution of theta depends heavily on lambda, right? And the bigger lambda gets, the more information for theta is given. Actually, information is a difficult concept in this, but relatively speaking, if we were doing it in maximum likelihood sense, the information function for this item is lambda squared over psi squared, right? It's constant, which means the larger lambda is relative to psi, the more precise or the more information this item is carrying about theta. Why does that matter though? Because if I wanted to cheat psychometrically, particularly when you think about industry, we have a psychometric industry that sells thetas to people. We do. And they have to bury in there, and I say this because it happens almost everywhere, in their technical manual, which only I read, I think, they bury information about the standard, the precision with which theta is measured. Sometimes goes by conditional standard of error of measurement, sometimes by reliability indices. Both mean the same, relatively the same, opposites of each other. How much precision do you have? So you could quickly claim to have more precision about theta if you were to inflate the value of lambda. And in the Bayesian sense, how could you inflate the value of lambda? Pick a prior where the mean of lambda is big relative to what the mean of psi should be. And sure enough, it will look like you have a ton of information about theta. Right? So I propose, and I mean this, the opposite. I pick a prior that does the least amount of harm. Right? I say for lambda, the mean should be 0. Right? If you have a 0 for the lambda, that means that item provides no information about theta at all. And so what happens here is again, I have a big variance, so let's not worry about that yet, but if the prior is causing shrinkage, it's causing shrinkage to have to claim that we have less information about theta than we really do. And to me, that's not lying with data, particularly when we're in the business of selling thetas. I mean that. I'm very passionate about that too. Go grab the technical manuals of the assessments that either you've worked on or taken before and read how they report how the accuracy of theta is. There's a reason your GRE didn't give you a conditional standard error of measurement. You two may have had the same score and paid the same amount of money, but one of you may be more precise than the other. It's a problem, right? Anyway. So, What you'll see in the we're going to talk more about priors when we get past standardized factor, but you'll see some people try to figure out a different name for this, and I don't like it in psychometrics. Do no harm. Claim the least amount of information about what you do. So factor loadings, discriminations, I say is normally distributed, mean of 0. I have a huge variance on that. Item intercepts, mean of 0. I have a huge variance on it. And then I did unique standard deviations with an exponential 0.01. Here's what I'm looking at. This is a plot. Actually, this is standard deviation 100. Yeah, variance 1,000. That's not right. Anyway, take a look at, you can see a curve here, but take a look at the scale of the y-axis. From the range that we might expect this factor loading to be in, the difference from the influence of the prior is only in the 3rd decimal place, right? Actually 4th, 10, 100,000, right? The 10,000th place. So it's a fraction of the information that we're pushing on the prior. Likewise, look at the exponential. Yes, it looks like a straight line. That looks terrible until you realize we're again affecting things in the 4th decimal place. It's only a small amount that we're playing with. Sound good? So I'm going to wrap up here and say, here's all the code, here's the model CFA, and we're going to leave off and start tomorrow with sampling. Right here. Start tomorrow. Start Friday. Okay? It's 1:45. I appreciate your being here. Thanks to everybody online. Thanks for hearing my stories and all the bad jokes, even if they're old. At some point, you just embrace the age. Actually, life is like a roller coaster, right? And at some point, it's like you're just holding on the way down, and that's where I'm at. All right, take care, everybody. On that note, have a very good rest of your day. See you, everybody.